Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 4, Integrals. Section 4.9 and 5.4, Antiderivatives and the Indefinite Integral.
Lesson 3, Properties of Indefinite Integrals.
Okay, so the next thing that we're going to talk about is properties of the indefinite integral. And the first thing I want to discuss is something that's sort of an interesting problem. Let's look at this example and notice what it is. I am being asked to take the derivative of something. I have my derivative operator notation here. And what's inside the square brackets? What am I being asked to find the derivative of? Well, what's inside the square brackets is actually an integral. So if I kind of work from the inside out, the way that I would do this problem is to say, well, I'm being asked to find the derivative of something, and that something is the integral of x to the fourth dx. Well, can I figure out what this is? That is an integral I know how to do because it's a power of x. Let's go ahead and do the integral that's inside these square brackets and see what the heck it is that I'm asked to actually find the derivative of. Well, the integral of x to the fourth dx, we know that we add 1 to the exponent, so I get x to the fifth, and then I need the reciprocal of that, 1 over that new power out in front, so I need a 1/5 in front, and then of course I could add on any integration constant c. But now I'm asked to find the derivative of that. So I'm going to go ahead and find the derivative. Okay, so the 1/5 is a constant multiple. That gets carried along. I take the derivative of x to the fifth and get 5x to the fourth. And I take the derivative of a constant. I get 0. And what do I end up with? These 1/5 and the 5 cancel out. I end up with x to the fourth. This is sort of interesting. I look in here and I notice that the function that I was originally asked to integrate was x to the fourth, and my answer here is x to the fourth. So what happened? I started with a function. I integrated it. In other words, I found the set of all antiderivatives of it, and then I went back and differentiated it, and I got back to the very function I began with. And really, we should have been able to guess this. We shouldn't have had to go through all of this in order to get the answer of x to the fourth. Because after all, what does the integral of x to the fourth dx mean? It means that I'm being asked to find the set of all antiderivatives of x to the fourth. In other words, I'm looking for all functions whose derivative are x to the fourth. So this means find all antiderivatives of x to the fourth, i.e., in other words, find all functions, I'll abbreviate functions here, whose derivative is x to the fourth. Okay, so when we just look at what's inside the square brackets, we're being asked to find all the functions whose derivative is x to the fourth. But then we're asked to differentiate those functions. So remember, the d by dx means differentiate, or I'll say find the derivative. Find the derivative of whatever's in the square brackets. In other words, find the derivative of functions, a set of all functions whose derivative, put that in brackets, whose derivative is x to the fourth. So we're being asked to find the derivative of a set of functions, each of whose derivative is x to the fourth. Well, if you find the derivative of something whose derivative is x to the fourth, you're going to get x to the fourth. So all of this is to say the following. If you start out and you integrate a function, here we integrated x to the fourth, we got 1/5 x to the fifth plus c. And then step 2, you go back and differentiate it. So then we went back and took the derivative of it. You are going to exactly undo what you just did. I'm going to fill in this blank here with undo. You'll undo what you just did. Here you're asked to find the antiderivative, then you're asked to go back and differentiate that antiderivative. You're going to get back to where you started. So what we often say is that differentiation and integration are like reverse processes. They undo each other, or oftentimes we say they are inverse processes. They exactly undo each other. And that should just sort of make sense. You're asked to find an antiderivative of this, you find it, then you're asked to differentiate that, you are going to get back to where you started. I'll say back to where we began, or where we started. And let's just write that fact down in general in this little square that's down here. If I start with any function f of x and I integrate it, that means I'm finding the set of all antiderivatives of little f of x. And then I go back and differentiate those functions whose derivative is little f of x, I'm going to get back to where I started from. Namely, I'm going to get back to little f of x. So we often say in a kind of a sloppy sort of way, but it helps us to remember that integration and differentiation, they undo each other. They're inverse processes. In a sense, they cancel each other out so that you end up back where you started at, namely, you end up back at whatever function little f of x you began at. If this is x to the fourth and you integrate and then differentiate, you'll end up back at x to the fourth. Okay, well, let's look at some other properties of indefinite integrals. So let's go ahead and think about something from the past for a moment. We had certain rules of differentiation. For example, here was the rule that the derivative of a constant multiple times f of x is equal to, and remember what we can do when we have a constant c multiplying some function f of x, and we're asked to find the derivative, we can pull that constant outside of the derivative operator. So this would be the same thing as c times the derivative of f of x. For example, if we looked at something like the derivative of 8x squared, well, 8 is a constant multiple, and although we don't usually write this step, we can pull this 8 outside of the derivative operator and say that's the same as 8 times the derivative of x squared. We've done this type of thing so many times that we don't usually write this step, but that's the rule that we are using, the constant multiple rule. And then we go ahead and say, oh, okay, that would be the same as 8 times, and the derivative of x squared is 2x, and so I end up getting 16x as an answer to that example. Well, it turns out that you can do exactly the same thing with integrals. So, for example, if I am asked to integrate, in other words, find the set of all antiderivatives of 7x to the fourth, 7 is a constant multiple times my x to the fourth, and I'm allowed to take that constant of 7 and pull it outside of the integral sign. So this would become 7 times the integral of x to the fourth dx. And of course, this is something that I know how to do from the power rule, so I would end up getting 7 times whatever the integral of x to the fourth dx is. And we know from the power rule that that would be an x to the fifth. I add 1 to the exponent, and then I do the reciprocal of this new exponent in front. So I would have a 1 over 5 in front, and then add on my integration constant. So I would end up with an answer of 7/5 x to the fifth plus c. Well, I just told you that we were allowed to do that for integrals. I haven't proved it for integrals. Back when we were doing derivatives, we proved this rule works when you're taking a derivative. We haven't proved it for antiderivatives yet. So the question becomes, how can I check this claim that I'm allowed to just pull this constant multiple outside of the integral sign? Well, the nice thing about integrals is that if I have something that I think is the answer, I can always check it by going back and differentiating. So how can we check our claim? We can go back and differentiate our answer. I'll say our claimed answer. So anytime I think some rule might be true, I can always check it by going back and differentiating. So I'm going to go ahead and take the derivative of what I'm claiming is the answer, 7/5 x to the 5th plus c, and I'll see whether it works. Well, when I take the derivative of 7/5 x to the 5th, remember that 7/5 is a constant multiple. So using our constant multiple rule for derivatives, which we proved back in an earlier section, this would be the same as 7/5 times the derivative of x to the 5th is 5x to the 4th, and of course the derivative of any constant would just be equal to 0. So that c drops out when I take the derivative, and I can see that these 5's cancel, and so I do get 7x to the 4th, and that does match what I was originally asked to integrate. So these match, and that means that I've checked that my answer was correct. So at least we've checked it for this one example. We've proved for this one example that you're allowed to pull that constant multiple of 7 outside the integral sign. But we'd like to prove that in general. Well, let's just go ahead and write down in general what we just said for this specific example, and then we'll try to prove it. So I'm saying that the integral of a constant times f of x dx is the same as, let's try to fill in the right-hand side. If this same rule works that worked in this specific example up here, I could take this constant multiple c times f of x, I could pull the c, the constant, outside of the integral sign, and it would be the same thing as c times the integral of f of x dx. Usually we don't write the dot in there when we jam them together, we mean c times that integral. Well, is that actually true? That would be called the constant multiple rule for integrals, but we haven't proved it yet in general. So we're claiming that this is the answer. So this is the claimed answer. How do we prove the claimed answer in any integration problem? Well, exactly the way that we did for this specific example, we go back and we differentiate our claimed answer. So let's do that. I'm going to go ahead and take the derivative of this right-hand side, the thing that I'm claiming is correct. So it's the derivative of c times the integral of f of x dx. Well, this is c times this integral. So c is a constant multiple, but now it's a constant multiple in a derivative problem. And we already had a rule for derivatives that said with a derivatives constant multiple of a function in a derivative problem, we're allowed to pull the constant outside of the differentiation symbol. So I should be able to pull this outside of the derivative operator, and that's using a rule that we already proved in an earlier section, rule of, I'll put constant multiple rule. Rule of differentiation. So we're using something that we had in the past that says, oh, by our constant multiple rule for derivatives, I can pull that constant multiple outside. Okay, so this thing should be exactly the same as c times the derivative of what's left. And the only thing that's left inside is this integral, because I pulled the constant multiple of c out. So it's the derivative of the integral of f of x dx. And that's all that's left inside of my square brackets. Okay, that looks good. Well, but now let's think about it a little bit further, and I want you to think about this expression that I have right here. I'm going to put the c times, carry that down from the line above, and what is the derivative of the integral of f of x dx? Well, remember at the very end of the previous page we said that if you integrate f of x and then you go back and take the derivative of that answer, those two processes are inverse processes. They undo each other. So essentially we say that integrating and then going back and differentiating undo each other, or roughly they cancel each other out. So all of this stuff is just equal to f of x. Okay. So this first step where we pulled the constant out was from the constant multiple rule of differentiation. This second step was the fact that integrating and differentiating our inverse processes, I'll say, undo each other. And now look what we have as an answer. We have c times f of x. So when we went back and checked our claimed answer, we went back and differentiated, we got c f of x, which is exactly what we had in our original integral. These match. And so we have checked that this must be the correct answer. Our claimed answer is right. And so the constant multiple rule holds not only for derivatives, but it also holds for integrals. You can pull a constant multiple sign outside of the integral sign. But let's do some examples so we can just get used to this new integration rule. And it's very simple to use, because it's very similar to what we did with derivatives. So suppose I asked you to integrate negative 4x to the 11 dx. Well, the negative 4 multiplies the x to the 11, so I'm allowed to pull that negative 4 factor outside of my integral sign, and it's the same as negative 4 times the integral of x to the 11 dx. And of course, we know how to integrate x to the 11 because it happens to be a power of x. So let's use our power rule. I'm going to add 1 to the exponent. I'll have x now to the 12th power. And then remember, we need the reciprocal of that new power out in front. So I need 1 over 12 out in front. And then I can add on my integration constant. And then it's just a matter of simplifying. Negative 4 times 1/12 would be equal to negative 1/3 x to the 12 plus c. And if we're not positive that we've done everything correctly, we could go back and differentiate this answer and check to be sure that we get a derivative of negative 4 times x to the 11. I'll leave the check to you. Okay, I'd like you to try the next 2 problems, so pause the video, give them a try, and if you get stuck, just go ahead and restart the video and we'll do them together. Okay, well, this first one's a little bit difficult because I have 60 divided by x cubed, and remember that although we have a power rule, it's not a power rule for x's that are in the denominator of an expression, and there is no quotient rule for integrals. Let's try to rewrite this a little bit first. I'm going to rewrite it in the following way. I'm going to write it as the integral of 60 times, and let's pull the x to the third up into the numerator of this expression, and that would make it an x to the negative 3 times dx. So that looks a little bit better because at least this is now a power of x instead of the power of x being down in the denominator. The 60 is a constant multiple, so I get to pull that outside of my integral sign. So I would get 60 times the integral of x to the negative 3 dx. And so now all I have to do is use my power rule on this part of it, x to the negative 3. Remember, we're adding 1 to the exponent, so negative 3 plus 1 would be a negative 2. And then I need the reciprocal of that new power out in front, so I need a 1 over negative 2 out in front. And then I have to remember to add on my integration constant. So it looks like, just simplifying this, I would get a negative 30. We don't like to have a negative exponent in our final answer, so I'm going to write it as over x to the positive 2 plus c. And of course, to check this, again, you could go back and differentiate, but I'll leave that for you to check. One thing I just wanted to mention is that oftentimes we don't write this step as you get used to it. At first, it's probably, I'll say, don't have to write this step. Oops, right. This step. So oftentimes we just think it in our heads and we go straight from here to here and we say, oh, if I want to integrate 60x to the negative 3, I can carry along the constant factor of 60 and I can just integrate x to the negative 3 and get negative 1/2 x to the negative 2 and then add on my plus c. So we often say the words, we carry along the constant multiple and then just multiply by whatever the integral of what comes next is. Okay, well, let's try this one, integral of 5 dx. That looks sort of weird because there's no x's in the function that I'm being asked to integrate. Now, there are two ways to go about doing this one. One is just to think backwards and think, well, what would I have to start with so that if I differentiated my thing that I write over here, I'd end up with 5 as an answer. And so you might just be able to think backwards and think, well, if I started with a 5x, when I differentiate 5x, I do get 5. And then just remember to add your integration constant on. So that would be one way to do it. The other way to do it, if you want to, is to use our constant multiple rule, and you could really think of this as the integral of 5 times 1 dx and pull this 5 to the outside. So that is a constant multiple, and I could write that as 5 times the integral of 1 dx. And we discussed this integral before, and again, there are two ways to do it. You could actually do it using the power rule by thinking of this as 5 times the integral of x to the 0 dx, although that's a rather complicated way to do it, but 1 is the same thing as x to the 0. So you could do it that way, or you could just remember, oh, the thing that I have to start with so that when I differentiate I get 1 would be an x plus c. So either way, usually in one that's this simple, that's just a constant such as 5, if you're asked to integrate it, we usually just think backwards and think, oh, I need a 5x here, so that if I were to differentiate my answer, I would end up matching that 5 that I was originally asked to integrate. Okay, well, let's go ahead and look at some more properties or rules of integration. And here's another rule that is also similar to our rule for differentiation. And this is a claim. We're going to have to prove that claim. I claim that the sum rule works not only for derivatives, but also for integrals. You might remember that when we were talking about derivatives, we said that the derivative of a sum of two functions is the same as the sum of the individual derivatives. Eventually, we learned to call that differentiation term by term. So we could differentiate each term separately and just add those together. So I claim that the same rule holds for integrals. In other words, when I integrate this kind of complicated function, f of x plus g of x dx, I can break that down into two simpler integrals and just add the answers together. I can do the integral of f of x dx separately and then add on whatever I get when I integrate g of x dx. And in words, we use words very similar to the words that we used for the sum rule in differentiation. We say the integral of the sum equals, and what do you think goes on the right hand side? The integral of the sum equals the sum of the individual, if you want to put that in parentheses, the individual integrals. But usually, because it sounds nicer, rhythmically we say the integral of the sum equals the sum of the integrals. Well, how do I prove it? I prove it exactly the same way I prove any rule of integration. I just go ahead and say, well, this is what I am claiming is the answer. So that is my claimed answer. And if I claim that's the answer, I can check it by going back and differentiating. So what I'm going to do is take what I'm claiming is the answer, differentiate it, and make sure that it gives me the function inside here that I was originally asked to integrate, f of x plus g of x. So let's try that. I'm going to go ahead and take the derivative of what I'm claiming is the answer, integral of f of x dx plus the individual integral of g of x dx. Okay, well, now I'm doing a derivative problem. I'm taking the derivative of a sum of two things. So now I can invoke the sum rule for derivatives. So I'm going to say, by the sum rule for derivatives, by sum rule for derivatives, which is a rule that was proved earlier when we were talking about derivatives, I'm allowed to break this up. We just got through reminding ourselves that the derivative of the sum is the same as the sum of the individual derivatives. So by the sum rule for derivatives, something that we had earlier, this would be the same as the derivative of this first term plus the derivative of this second term. So derivative of the first term plus the individual derivative of the second term. Okay, great. But now let's look at each of these terms that I have left. If I look at the first one here, I have f of x, then I integrate it, and then I differentiate it. I'm taking the derivative of the integral of f of x. And remember that we said by that fact that integration and differentiation are reverse or inverse processes, they undo each other, what would all of this be equal to? Well, it would just be equal to f of x. And that's because integrating and differentiating undo each other. Essentially, they cancel each other out as processes. Well, I have a plus sign between these two things, but what about this? What would that simplify to become? I have g of x, I'm integrating it, then differentiating it. By exactly the same argument, these two things undo each other, and I'm left with simply g of x. And so I end up with f of x plus g of x as a final answer. And notice that's exactly what I was originally asked to integrate on the left-hand side. So these two things match each other. And that means that my answer must be correct, that this thing must be essentially the answer to this integral problem, and I've proved the sum rule for integrals. Well, let's go ahead and we'll try to do an example. So here's an example for us to try. And what we say, just like with derivatives, we say we can integrate term by term. So I'm going to show all the steps, although in practice, as you get used to this, you won't have to show every step. The integral of x to the fourth plus x squared. So here we have two functions that are added together, and what our sum rule says is that we can go ahead and integrate these separately. So the integral of this sum is the same as the sum of the individual integrals. And let's go ahead and see what that would be. Integral of x to the fourth, that's something I've already done. I can use the power rule, add 1 to the exponent and put a 1/5 out in front, and I'm going to put plus c1. So I've integrated this and I've added its integration constant. And remember, c1 ranges over all real numbers. We think of it as being all possible real numbers from minus infinity to infinity. Okay, plus, now I do this integral individually. Integral of x squared dx, well, I add 1 to the exponent using the power rule, so that'll be an x cubed, and I need the reciprocal of that new power out in front, so I need a 1/3 out in front, and then of course it has its own integration constant. Maybe I'll call that c2. Let me just rewrite this by reorganizing the order of these terms. I'm going to put the x terms together, so 1/5 x to the fifth plus 1/3 x cubed, and I'm going to put these integration constants together at the end. What I want you to do is to think about the fact that c1 ranges over all possible real numbers, and c2 ranges over all possible real numbers. If I looked at these two things together and thought of them as individually ranging from minus infinity to positive infinity, their sum would also eventually cover all numbers from minus infinity to positive infinity. So c1 plus c2 would also range over all possible real numbers from minus infinity to infinity. There's no real reason to write c1 plus c2. I could write a single integration constant of c on here and say, okay, I'm adding on c, where c is any real number from minus infinity to infinity. Because c1 plus c2, eventually as they range individually over all real numbers, their sum will range over all real numbers. And so we never write two integration constants this way. We always write just a single integration constant at the end. So my answer would be 1/5 x to the fifth plus 1/3 x cubed plus c. Okay, so let me just make a couple remarks about this. Usually we don't write this step. We just say, oh, I can integrate term by term. I integrate x to the fourth, I get 1/5 x to the fifth. I integrate x squared, I get 1/3 x cubed. And we say that we integrate each term separately. We integrate term by term. And then we just add a single integration constant on. There's no point in adding two integration constants because as they range over all real numbers, their sum does also. So we usually don't write these two steps once we get used to the sum rule, and we just go straight. In fact, we don't even write this step once we get used to it. We just go straight from here down to here, integrate term by term, and then add the integration constant onto the end. One thing I want to mention before we leave this page, we wrote this down as the sum rule for integrals, but there's also a difference rule for integrals. So I'm going to put or, if I can get my pen to work, I guess that one doesn't want to. I'll put or, and that one doesn't want to, okay, or difference rule. So this also works if I'm doing the difference of two functions. In other words, if I had f of x minus g of x dx, and I was asked to integrate that, it would be the same as the integral of f of x minus the integral of g of x dx. So just like with derivatives, it doesn't matter whether I'm adding my terms or subtracting my terms, we can integrate term by term. Well, let's do a few more examples so we can get used to this idea. Let's do this example together, and then I'll ask you to do the next one yourself. Here I have a difference of terms and then a sum. So what we're saying then is that we can integrate this term by term. I'm going to write out that extra step here so that we can see exactly what's happening. And I encourage you to write these extra steps at first, and then as you get used to doing this, you can drop some of the extra steps. But just so that we can see exactly what we're doing and exactly which rules of integration we are using, I like to show all of these steps. So the integral of a difference is the same as the difference of the integrals. And I can integrate each of these things. The integral of this sum is the same as the sum of these integrals. So I can integrate this polynomial term by term. Also, I notice that I have some constant multiples. In this integral problem, I have 8 times x cubed. What can I do with that 8? I can pull it outside of the integral sign. So that would be the same as 8 times the integral of x cubed dx. This 6 times x, another constant multiple, so since 6 is a constant and a multiple, I can pull it outside the integral sign. And then I'll just leave this as integral of 1 dx. All right, now we've gotten down to doing integrals of things that are powers of x, and so that means I can use my power rule. So we've gotten down to simpler functions that we know how to integrate. Okay, integral of x cubed, I add 1 to the exponent, that gives me x to the 4th, and I do the reciprocal of that new exponent out in front. The minus 6, that factor gets carried along, and now I want to integrate x dx. Remember, I could write this as a power by putting an exponent of 1 there. So I add 1 to 1, I will get x to the 2nd power, and then I'll have a 1 over that new power out in front. And this last one, integral of 1, I usually just think, what do I have to have here so that when I differentiate, I would get a 1, and I have to have an x. I usually just think backwards there. And we could add a C1 plus a C2 plus a C3, 3 separate integration constants for those 3 terms. But as those 3 integration constants, C1, C2, and C3, range over all real numbers from minus infinity to infinity, so does their sum, C1 plus C2 plus C3. So we always just add a single integration constant onto the end. And then I just simplify. This would be a 2x to the 4th. This would be a 3x squared and a plus x plus c. And that was kind of a long process, so if I wanted to check it, how would I check it? Remember, you can always check by going back and differentiating this. You can do it in your head if you want to, and just be sure that you end up getting this polynomial. If I do it in my head, I'd be thinking, oh, 2 times the derivative of this would be 2 times 4x cubed. That's 8x cubed, so that checks with this term. And this one, I'd say negative 3 times derivative of this is 2x. Negative 3 times 2x would be a negative 6x. Derivative of x is just 1, so that checks. And derivative of any constant is just 0, so that would drop out when I differentiate. Okay, I would like you to try the next one. So pause the video, give it a try, and then we'll go through it together. Okay, let's try this together. So, in this case, yeah, I can integrate term by term. I have this term minus this term, so it is really the integral of this first term minus the integral of this second term. And with this second term, I notice there's also a constant multiple, so I could pull that out. Let me do that. So this would be the integral of the 7th root of x cubed minus 12 times the integral of root x. And you may have done things in a slightly different order than I'm doing them, and that's okay. But now I have to ask myself, how am I going to integrate the 7th root of x cubed? really the only thing we know how to integrate are powers of x. Can I write that as a power of x? Yes, by using a fractional exponent. And what would that fractional exponent be if I'm raising x to the third power and I'm taking the seventh root? Well, remember the power goes in the numerator of our fractional exponent, and the root that we're taking goes in the denominator. A trick someone taught me is that they thought of roots as being something that grows in the ground, so it's below you. So the root goes in the denominator of our fractional exponent. And the same thing over here. This is really, a square root really means the index is 2. We just don't write it because we use square roots so often. So this would be x to the 1 over 2. X is raised to the first power, and we're taking the second root. Great, now I can use the power rule to find each of these remaining integrals. So let's see, x to the 3/7. I have to add 1 to that. You can always do it on scratch paper over here. I'm adding 1 to this. That would be 3/7 plus 7/7 if I write 1 with the same denominator. So that's going to be an x to the 10/7. That's my new exponent. And remember, we need the reciprocal of that out in front. We need 1 over 10/7, which is the same as 7 over 10, the reciprocal of that new power. And then I'll have minus 12 times, and 1/2, if I add 1 to 1/2, that would be a half plus 2 over 2. That would be x to the 3/2. And then I need the reciprocal of that new power, 2/3, out in front. And I add a single integration constant onto the end. So what do I have? I have 7/10 x to the 10/7 minus, let's see, that goes in 4 times, 8x to the 2/3, I think that's right, plus c. And usually if our original problem used root notation rather than fractional exponents, then we like to write our final answer using root notation. So this is probably acceptable to most instructors, but the nicest way to write this would be as roots. This is the 7th root of x to the 10th. That actually does reduce. You can pull an x out, and I believe you would then have an x cubed left inside. Yeah, so it should be the 7th root of x times itself 10 times. 7 of those makes up 1x that you can pull out, and you have 3 of them left over. Okay, and this would be minus 8. This one's a little easier. It's just the cube root of x squared, and you can put this power of 2 either under the root symbol or outside of it. So this would be the very nicest way to write your final answer. Okay, let's go ahead and look at the next page. We have a couple more examples to try. And I think on this page, I wanted you to give these a try yourself. But before you start this one, I want to remind you that although there is a sum rule and a difference rule for integration, there is no product rule. So remember that there's no product rule for integrals. In other words, you could not do something such as integrate this cube root of u and then integrate u plus 1 separately and somehow multiply them together. This is a product of 2 functions, cube root of u times the function u plus 1, and we have no product rule for integrals. There's nothing that says that we can integrate factor by factor. We can integrate added term by added term, but not multiplied factor times multiplied factor. And on this one, if you want to think about that as well, just remember there is no quotient rule for integrals. And so we are not allowed to, for example, integrate the top and then divide by the integral of the bottom. There's no such rule, and it would actually give us the wrong answer. Oh, by the way, I said there's no product rule for integrals. Actually, in second semester calculus, you do learn a rule called integration by parts. It's one of many techniques of integration, and that is based on the product rule for derivatives. So there is a sort of product rule for integrals, but not something that we've dealt with at this point or will deal with in this particular semester of calculus. It's really a second semester calculus problem. So pause the video and think about these two problems. See if you can find a way around the fact that this is a product and this is a quotient, and we have no product or quotient rule for integrals. See if you can do them. If you get stuck, just start the video and we will go through it together. Okay, well, let's look at this first example. We said there's no product rule for integrals. I'm not allowed to just integrate cube root of x, integrate u plus 1, and multiply the answers together. It will not give me the correct answer. However, I could distribute this out. Now, before I distribute this to each of these terms, let's go ahead and rewrite it. I think it would be easier to work with if it were a fractional exponent instead of a root. So before I distribute it out, I'm going to write cube root of u as u to the 1/3 power. And then I'll distribute it out. So what we're doing right now is not integrating, but we are first rewriting to get it into a form where we can integrate. Now I'll distribute this out. So remember that when I multiply u to the 1/3 times u, I could put an exponent on here of 1. And when I do u to the 1/3 times u to the 1, I'm multiplying like bases, so I'm supposed to add the exponents. So it's going to be u to the 1/3 plus 1. So that would be u to the 1/3 plus 3/3 is 4/3. And then when I multiply u to the 1/3 times 1, I just get u to the 1/3. And that looks like something that we're going to be able to deal with, because now instead of having a product of two functions, I have a sum of two functions, and I'm allowed to integrate, sometimes I'll abbreviate it this way, integrate term by term. So term by term. So now we're allowed to integrate term by term. And let's go ahead and use the power rule on each of these. Let me write the step in between here, although this is a step that we will probably drop after you've gotten a little more practice with the sum rule. I get to integrate term by term, so I'm doing the integral of u to the 4/3 du plus the integral of u to the 1/3 du separately. Here I get to use the power rule, so I'm going to add 1 to the exponent. 4/3 plus 1, that's 4/3 plus 3/3 would be 7/3. And I put the reciprocal of that new power out in front. And I integrate u to the 1/3, so 1/3 plus 1, that's 1/3 plus 3/3, that would be 4/3. And I put the reciprocal of that new power 3/4 out in front, and I add on a single integration constant. At the very end, since our original problem used the root notation instead of fractional exponents, it would be nice to write this with root notation instead of fractional exponents. And I believe here we would get 3/7. This is the cube root of u to the 7th. I believe that it will reduce to a u squared times the cube root of, let's see, we would have 1u left over. So 6 of the cube roots of u become 2u to the 2nd outside, 2 factors of u outside, and then we would have a cube root of u that's left over. You can check that. I know I'm going through that quickly. And the same thing here, this is the cube root of u to the 4th power, so cube root of u times itself 3 times would give me 1u on the outside, and I would have a cube root of u left over, and then I have to add my integration constant, my plus c. So that would be the very nicest form for the answer. I would probably accept this answer as well, using the fractional exponents. Okay, how about the second one? Is there a way to rewrite it so that we no longer have a quotient? Since we have no quotient rule for integrals, can we rewrite it? Well, yeah, we could. In this case, we luck out because we have a single term in the denominator. And what that means is that I could think of breaking this up. Instead of a single fraction, I could think of it as 3 fractions, each of which has a common denominator of x to the 6th. So the way that I would approach this problem is to say, well, this is the same as 20x to the 9th over x to the 6th. Let me put some brackets on here. Plus the next term in my numerator, 3x squared over x to the 6th, minus 10 over x to the 6th. So I've just broken it up into 3 fractions. I know that usually we take these 3 fractions, add them together and say, oh, they have a common denominator, let's write it as a single fraction. We're sort of doing that process backwards. And I can do that specifically because I have a single term in each of the denominators, and so I'll be able to simplify each of these fractions that I have left. So let's see what we end up with. If I simplify this portion of it, I would have a 20x cubed. And this, let's see, if I subtract exponents, I'll have 2 minus 6. So 2 minus 6 would be x to the negative 4. And here I would have an x to the negative 6th if I write it as a power of x. So that's nice. Now instead of having a quotient, I do have sums and differences. I have individual terms, and I'm allowed to integrate term by term. When I integrate this term, I have a constant multiple of 20. So I can pull that 20 outside of my integral sign and write it as 20 times the integral of x cubed. And when I integrate this second term, I'll have a constant multiple of 3. So I can pull that outside the integral sign, and all I have left to do is to integrate x to the negative 4 dx. And here I have a minus, and when I integrate 10x to the negative 6, again the 10 is a constant multiple, it can come outside of the integral sign, and I would get 10 times the integral of x to the negative 6th dx. And now everything that's left in the integrals are just powers of x, so I get to use my power rule. So I'll have 20 times integral of x cubed, we've done that a few times, x to the 4th, and a 1 over 4 in front, plus 3 times integral of x to the negative 4. Remember, you're adding 1 to the exponent. Negative 4 plus 1 is negative 3, and then I need the reciprocal of that new power out in front. And then minus 10 times integral of x to the negative 6th. I add 1, I'll get x to the negative 5, and I would have a 1 over negative 5 out in front. And I add 1 single integration constant onto the end. Then it's just a matter of simplifying a little bit. Let's see, this 20 times 1/4 is 5x to the 4th. And 3 times negative 1/3 would be minus 1. And I'm going to write the x to the negative 3 as x to the positive 3 in the denominator. So far I have 5x to the 4th minus 1 over x cubed. And for this last one, let's see, negative times negative will become a positive 2, but I want to write this with a positive exponent, so 2 over x to the 5, x to the positive 5, and then there's my integration constant. And so that would be the nicest way to write my final answer, if I can squeeze a box into there. And of course, on all of these, you can go ahead and check by differentiating, but just be aware that when you differentiate something like this, it won't look exactly like your original problem. It will actually get you back to this stage where you had it written as separate powers of x. So you can at least check it back to that stage, and as long as you simplified up to here correctly, you're all set. Okay, let's go ahead and think about our next